I'm here to take you on a trip full of high screeching sounds and mind-blowing physics. Let's see, where do I start? Right, you see this plastic tube in my hand? It looks like a cheap plastic toy that you find at the dollar store, but it's much more than that, believe it or not. Here, just take a listen. Simple enough, right? I mean, what else can you do with it? Wait, I can do more. Man, that's tiring. Maybe we should take a break. Okay, I'm good now. Now let's get down to business. Now look at this fine piece of plastic. Now look at the air around you. And you put them together, what do you get? You get sound. What I mean is, in order for this tube to make sound, air must go through it. And this can be explained through the Bernoulli's principle. As the air goes through, the molecules are bumping along the little ridges inside and they're creating little vortices. I know, vortices, crazy, right? Anyways, in those vortices, there are standing waves. And standing waves are created when a wave is reflected from a point and the incident waves are interfering with those reflected waves, so it looks as if the wave is standing still. Now back to the tube, I'm always going to use the same tube, so it's going to stay the same length, and I'm always going to swing it in the same medium, which is the air around us. Like, for instance, if I were to go underwater and swing it for some reason, then the speed of the wave would be different. But I don't have enough time or the money to show you guys that right now. Okay, so based on the wave equation, you can see that the only thing I can change by myself is the frequency, and I can change the frequency by spinning it faster. The wavelength, on the other hand, after you go to the next harmonic, you just add half a wavelength, so I can't really change that. And it's not that easy to change the frequency to whatever number you want. It has to be an integer multiple of the fundamental frequency. And you can learn more about how to get that on my website, which is linked down in the description box. And when you spin it faster, you can tell that the pitch is also increasing. Listen. See, that's the first harmonic, and then the second one. Okay, you see it got higher and higher and higher, and that's because the higher the frequency, the higher the pitch. And this will keep going on and on and on, as long as you can spin it fast enough, and if it's the same, if it's the integer multiple of the fundamental frequency. Now, the same exact principle can be used in any type of instrument you can imagine. Well, most of them anyways. Like, for example, this guitar. It uses basically the same principle. Like, as I'm playing this, it's going to be the same guitar and everything. It's going to be played in the same medium. And the wavelength is going to depend on each harmonic. The only thing that can affect its different notes is the linear mass density, which is what it's made out of. Like, these are made out of different materials, so they have different sounds. And you can also adjust the length, and that would change a lot. And that's why they have different sounds and pitches. And if you had a clarinet, perhaps, or like a recorder, then it would depend on where you put your finger on the hole, because every time you put a finger on the hole, you change the pressure notes in the body of the clarinet. And that's it. And if you have any more questions, you can ask in the comments, or you can check out my website for more information. And thank you for watching. Oh, and remember, at my website, we have articles, and it's pretty neat.